before we go with the next speaker, people who are offered full-time support and also people who are offered part-time support. So thus clarification is already there through the mails that we have sent. People who are offered the full-time support, please provide your the tickets that you have used to come here, and then there'll be a form given to all of you where you have to give your full account details. I think you all know no cash transactions, nothing is allowed these days. Everything is online. So we will process your things and then directly put the money, credit the money into your accounts. So that I think while registration, one form is given to you. If not, you can just ask. You're not given. Okay, then Tarunya will be giving one form. Please fill the form with all your account details and all that. That will be used for in the office. We will process it and then let you know once the money is credited into your account. Okay. Any further clarity on this? Hope I'm clear. And then second thing is it's a bit late, but just wanted to say that the restrooms are on the right side over here. Water is also available through the dispenser, and we don't encourage getting any food or anything inside because this is all like sophisticated equipments under cable and all that being run. If any food falls here, rats and all can come and then they just can destroy the cables and all that. So we strongly discourage getting any food. So please maintain the same decorum of not getting a food into the classroom. We'll be having lunch in the same place where you all had your breakfast, and then your dinner also will be there itself. I think beyond this, if any other specific doubts you have, I can just clear. If not, these are the logistic things that I want to clarify. Okay, clear? Thank you.
Thank you, sir. He's a postdoctoral fellow in marine biogeochemistry at the Physical Research Laboratory (PRL) at Ahmedabad. His research focuses on understanding the biogeochemical processes that affect carbon, nitrogen, and phosphorus stoichiometry in seawater and coral of the tropical area. At PRL, he is also engaged in mesocarbon-based experiments investigating ocean alkalinity enhancement as a potential carbon dioxide greenhouse gas. He earned his PhD in isotopic geochemistry from IIM Bhopal, where he studied estuarine biogeochemistry and groundwater systems along the eastern coast of sulfur carbon using trace methods and radiogenic items. So welcome him and let's hear.
That's okay. Thank you, Tesita. Hello, everyone. Welcome to my talk. And thank you very much to the ECOP India Node Committee, DDC, IOR, Inquires for providing me this wonderful opportunity. So today I will be discussing about blue carbon and marine carbon dioxide removal technique, pathways to mitigation. That is most discussed topic as well as most controversial in terms of what would be the consequences of carbon dioxide removal in future. So my talk is aligned with the goal of the UN Ocean Decade. So that is unlock ocean-based solution to climate changes. So as we all know, we stand at a critical juncture of the climate crisis. Like ocean has been proven to be a silent observer of the carbon dioxide since a long period of time, even on geological history. So nowadays, ocean are gaining very increasing attention due to not only because of victim of climate change, but it also looks like a vital part of the solution for this climate change. So carbon dioxide removal technique could be a very useful tool to remove the carbon dioxide. So through this talk, I will try to shed some lights on different type of mCDR techniques and how they are going to be worked. So first of all, start with a brief introduction about blue carbon. So blue carbon, what is blue carbon? Blue carbon is the carbon sequestrated by the plankton, algae. So they are ultimately stored in the coastal and marine ecosystem. So they could be in the form of biomass as well as they could be in the form of sediment. So when their detritus products are settled on the bottom of the coastal region. So they could be in the form of biomass as well as organism. So and ultimately these biomass are getting captured by the living organisms. So they are also part of the blue carbon. And this tiny environment that is coastal habitat play a very significant role. This key system include the tidal masses, mangroves, as well as sea grasses. So once they capture the carbon dioxide, and their detritus products are settled on the bottom. They are getting buried in the sediments. So the remaining product of mangroves forest as well as salt marshes, they could be buried for a longer period of time, even on 1,000 years of time scales. So they looks like a very vital solution for the sequestrating carbon dioxide. And this is a one map which is showing the spatial distribution of different blue carbon ecosystem like salt marshes, mangroves, as well as seagrasses. So you can see how much it is covering. It is cover only 2% of the total area of the land masses. So despite of very negligible coverage by this coastal blue carbon ecosystem, they are sequestrating the 50% of the carbon dioxide in their sediments as compared to the total carbon dioxide sequestrated in the ocean. So, and despite of this role, this system is at very high risk due to increased anthropogenic interventions like untreated water discharge. So they are causing the eutrophication and increasing biological oxygen demands. As such, they are causing the mortality. And also, we are delivering lots of sediment which are reaching to the coastal ocean. So they are also getting covered by these sediments. So, and further due to global warming, the sea level is also rising. So we are also losing in terms of sea level rise, this ecosystem. So as we know, so this is very popular diagram, which often seen by climate scientists. So this is the carbon dioxide measured at the Mauna Loa Observatory. So on x-axis, this is here, which is showing how carbon dioxide has increased from 1958 to present day. So you may see the carbon dioxide concentration has been increased in recent time from 1958 to present day, from approximately 300 ppm to 420 ppm, which is approximately 50% of the carbon dioxide has been increased since pre-industrial time. If you'll see on little bit on geological time scale, so if you'll see record how this has been behaved during last geological time. So this is the carbon dioxide level uh, uh, during last 1 million years. So the geological data has been retrieved from the ice core, whereas here these data are derived from the instrumental measurement. So despite of change in carbon dioxide concentration during geological past due to cyclicity in Earth orbit, this concentration has never crossed the 300 ppm. So, but if you will see in the recent decade, this carbon dioxide concentration has increases very rapidly. If you see from 1911 to 1958, and then after that to present day, how carbon dioxide has increased drastically. So, and because of that increase in carbon dioxide concentration and also other greenhouse gases, see how global warming has happening. So this is data for global global temperature anomaly with respect to the pre-industrial time, that is covered from 1850 to 1900. So with respect to pre-industrial time, you may see how much temperature has risen till date. So these blue point are the observed data, and how this expected to increase. We may see this is projected to increase by 1.5 degrees Celsius by 2032 and 2 degrees Celsius by 2057. So there will be huge impact of these consequences. So this is very interesting diagram, which is showing how much carbon dioxide has increased since 1850 only, not from beginning of other. So from 1850, you may see approximately so from 1850, you may see, so here black trends are representing the observed data, what we have instrumental record here. So from 1850 to 2019, we have accumulated the approximately 2,500 gigaton of carbon dioxide in the atmosphere. And because of that, we have the temperature in the atmosphere has risen by 1.5 degrees Celsius because of this increase in carbon dioxide. And further, this diagram also shows the different climatic policies which are going to affect the accumulation of carbon dioxide. So in worst scenario, that is SSP 5. So which is showing that by 2050, which is not very far, which is only 25 years from now, the carbon dioxide will be reached to up to 4,500 gigaton of carbon dioxide. What we have present day, what we have present, it will be just a double of this. So because of that increase in carbon dioxide, there will be the temperature will raise by 3 degrees Celsius. Just in 25 degrees, just in 25 years, the temperature will get doubles. So every tons of carbon dioxide anthropogenic emission, what we are adding to the atmosphere, that is leading to the global warming. So what would be the major consequences? Why do we care on land? So first of all, the potable water supplies, like as you know, because of global warming, the freshwater water bodies are shrinking. So water supplies will be also altered. And there is change in weather patterns. Like you may see nowadays, we are getting extreme rainfall, extreme hot conditions. So ultimately, they are affecting the uh, crop yield production. So they are affecting the food supply. And also we are getting the acid rain because of increasing carbon dioxide. Also sea level is rising. So that is ultimately causing that destruction of the coastal habitats, I mean geographical patterns in terms of land use and land cover. So not only we are getting affected, ocean ecosystem is also getting affected. So this is lower one, which is showing that how carbon dioxide has increased and how pH has get lowered from that time to the present day. So the ocean acidification is also happening, and because of acidification, the marine calcifiers like forams, as well as you might be heard coral bleaching. These things are happening right now. So we are losing this important living organism in the coastal as well as marine ecosystem. And this diagram, which is in the right upper corner, which is showing that how coastal as well as open ocean could be affected by warming. So because of warming, there will be thermal acidification that will reduce the exchange of atmospheric gases. So that will ultimately cause the reduction in oxygen exchange. So there will be prevalence of oxygen minima zone in the ocean. So that will ultimately affect the living organism. And also there will be because of thermal acidification, there will be reduced nutrient upwelling to the ocean. So that will ultimately cause the reduction in primary productivity, and reduction in primary productivity will cause the reduction in carbon uptake. And remember this, these phytoplanktons are the foundation of the marine food web. So ultimately higher trophic level will also will be affected. So because of warming, so many things are happening right now in the ocean. So we must protect this fragile ecosystem. So this is very popular diagram, which is often shown by the CDR peoples. So here on x-axis, this diagram shows the year and what would be the expected in change in carbon dioxide concentration by 2100. And on y-axis, this is showing the how much carbon emission is getting in the excess amount as compared to the removal. So at present day, we are at here, like we are at here. So we are approximately emitting the 10 pentagram of carbon dioxide, what as compared to the removal. So we are emitting the excess amount of 10 pentagram of carbon dioxide. So if there will be no climate policy, so this will follow this trend. So that will lead to the 600 ppm of the carbon dioxide and will lead to change in temperature by 5 degrees Celsius as compared to the pre-industrial time. So we need some climate policies, or we need some action. So because of Paris Agreement, after Paris Agreement Convention, we decided to achieve the net zero. What is net zero? Net zero is the condition when whatever we are emitting, this carbon dioxide emission must have been removed by some way, by some processes. So this is known as the balance condition of net emission to the net removal. So that is called net zero. So even though we are going to stop all those anthropogenic emission, so still we will not be able to achieve the net zero by 2100. Still there will be some residual emission. Why there will be some residual emission? Already we have altered the land use and uh, land cover patterns, and we already have produces so many chemicals which will emit the carbon dioxide or other greenhouse gases. So we will not able to achieve the net zero condition after eliminating all those anthropogenic emissions. So we need some extra carbon dioxide removal techniques. So how it could be removed? So carbon dioxide removal technique basically it's a method to sequester the atmospheric carbon dioxide to the ocean. So what would be the key benefit? Key benefit would be to protect from climate change, and that will also care about the ocean health. So we cannot remove the carbon dioxide. We cannot remove the carbon dioxide directly to any system. So there are certain criteria. Criteria are that system must be environmentally safe. We must care, and that approach should be socially acceptable as well, and that approach should be economically viable. That should not be too costly. So these are three main criteria to keep in mind. First, most important thing is that method should be environmentally safe. So here we have carbon is stored in different reservoirs. So you may see how much not carbon dioxide. So how much carbon is stored in the deep ocean and how much carbon is stored in other reservoirs. So as ocean holds approximately 37,000 gigaton of carbon, which is very high as compared to the other reservoir. Also to the atmosphere, which is 50 x more than carbon in the atmosphere. So it allowing us to store more carbon. So a small change in carbon inventory can lead to a large change in the atmospheric carbon dioxide. As such, ocean offers a vital solution to remove the carbon dioxide from the atmosphere to the ocean because of its big size. So we have different carbon dioxide removal techniques. So you might be heard about coastal and ocean blue carbon restoration. So here what we do, we increase the biomass production by photosynthetic activity, which is the biotic processes. So ultimately that will reduce the carbon dioxide from the atmosphere. And another thing is seaweed cultivation. So by doing seaweed cultivation, we are sequestrating the more carbon dioxide, and we are also ensuring the food supply. So these two things are biotic method, and here we have another thing is ocean fertilization method. Then we have ocean alkalinity enhancement and direct carbon dioxide capture from the ocean. So basically, we would be able to divide these different kind of marine carbon dioxide removal technique in two broad category. One is biotic, that is mainly dependent on the photosynthetic processes, whereas abiotic process involves the chemical kinetics. So to restore the blue carbon ecosystem, first of all, we need to restore the coastal wetland, as well as we need to protect this fragile ecosystem to be submerged because of rise in sea level. And we also need to restore the hydrological patterns in terms of riverine discharges. Like we are discharging huge amount of untreated water to the coastal regions, so that is ultimately causing the eutrophication in the coastal region. And we are also delivering the huge amount of sediments, what this is doing. This is bring the this fragile ecosystem. So and also we need to do some CVD aquaculture, which will also help. So the major problem is the strategic recommendation to scale up the uh, investment in the restoration of this blue carbon project, as well as incorporate blue carbon into the climate policy. This has been uh, very ignored system, as we can say. So another method is ocean fertilization method. So what is ocean fertilization method? Heard you might be seeing in the agriculture land. What we do to increase the crop production, what we do, we add the some fertilizer of the nitrate, phosphate, or other things. So photosynthetic process, what we have been teach right now, we have teach like just availability of carbon dioxide plus water in presence of sunlight, it will make biomass. So photosynthesis not happen in such a way. They require other essential nutrients like nitrate, phosphate, as well as other micronutrients. So if any of the nutrients will be missing, there will be no primary productivity, even though you are supply plenty of carbon dioxide to the system. So similarly, in the ocean, what we do, uh, as you know, most of the oceanic regions, particularly the low latitudinal regions, are limited by the availability of nitrate, whereas the high latitudinal, like Southern Ocean, uh, their primary productivity is limited by the availability of iron. We have carbon, nitrate, phosphate, everything is there, but iron is missing. So because of this nutrient limitation, primary productivity is low. So what we'll do here, just we add some nutrients to the ocean. If we are adding the nutrients to the ocean, what would happen? Primary productivity get enhanced, and that will ultimately sequestrate more carbon dioxide. And another method is ocean alkalinity enhancement. Here again, we are adding minerals, but process is different. The ocean fertilization was one type of biotic processes. Here, what we are doing here, we are not enhancing the primary productivity. Rather, we are just shifting the carbonate equilibrium towards the bicarbonate side, so that partial pressure of carbon dioxide in seawater should decrease, and that can sequestrate more atmospheric carbon dioxide into the ocean. So here we are adding some alkaline minerals which will dissociate and that will make carbonate and bicarbonate. So as such, this chemical equilibrium will shift toward the bicarbonate side, carbonate and bicarbonate side. So overall, what would happen? The partial pressure of carbon dioxide will be decreased, and this will sequestrate more carbon dioxide from the atmosphere. So this is known as ocean alkalinity enhancement method. And this method will also ensure and also ensure and will take care about the ocean acidification, because they are consuming the H plus ion. So, and another method is direct ocean carbon removal method. So here what we do, we collect seawater in certain reservoirs, or so we apply electricity, so it will dissociate in acid and base. So if you are adding acid in any of the water, so inorganic carbon dioxide will be liberated from. Like if you will add some acid, if you put some acid to the limestone or carbonate, there will be release of carbon dioxide. Similarly, there is a huge amount of carbon dioxide stored in the ocean. So if you will add some acid, so carbon dioxide will be liberated, and that carbon dioxide will be stored in the geological reservoir beneath the earth. So ultimately what happened, the carbon dioxide pressure, partial pressure of carbon dioxide in the seawater will be decreased, and that will sequestrate more carbon dioxide from the atmosphere. So I'm not going very much in different type of techniques. So here we have some techniques which I have not discussed. So this is the diagram showing the different types of carbon removal method, and cost as well as effectiveness involves with that particular type of carbon dioxide removal method. So in first quadrant, if you see ocean alkalinity enhancement as well as soil organic carbon, so we have very low cost is involved, whereas very low cost is also involved in the coastal blue system, but the system would be that much effective. So we can see ocean alkalinity enhancement is the most effective system in the given different kind of mCDR technique. So that's why most of the people have started working in this field, and they are testing by applying different kind of mineral in the mesocosm experiment, how alkalinity is getting changed if we are adding different kind of mineral with times. So overall, ocean alkalinity enhancements appears to be the most promising tool for carbon dioxide removal, but this ocean alkalinity enhancement techniques have different advantage, risk, as well as challenges. So major advantage, you may see this increase the carbon dioxide, this increase the carbon uptake without causing the risk of the ocean acidification, because it utilize the H plus ion. Also, this addition of mineral, this process also happens on geological time scales. Like you might be heard, Himalaya is contributing to sequestrating the atmospheric carbon dioxide since geological time. Like if we are weathering some rock, due to silicate weathering, there will be sequestration of carbon dioxide. So this process is already happening, but we cannot tell millions. We cannot wait till million severe time. So we need some quick removal process. So that's why we are applying manually some minerals to the ocean. So that process is already mimicking the natural process of rock weathering, and there are some risk involved. So risk involves if you are adding minerals, so alkalinity will be enhanced. There might be increase in pH. Because of increase in pH, there will be some precipitation of those carbonate and bicarbonate. So runaway precipitation is major issue with this technique. And another thing is whenever we are adding the some minerals to the certain point of the ocean, so at the point of addition, the concentration of that those elements or those chemical will be very high. So that could adversely affect the ocean biogeochemical condition. And challenges, what are challenges? Major thing is that if we even if we adopt this technique, how we'll monitor and how this system is responding, how we'll check. These things are major issue: monitoring, verification, as well as their response. So we need some high resolution of climate model or carbon model which can which can mimic the scenario of the uh, ocean alkalinity, ocean alkalinity enhancement. And we also need to um, ensure the scalability of the ocean alkalinity enhancement. How much that technique is removing the carbon dioxide. So this is another issue. So these are three main points related to ocean alkalinity enhancement, that is advantage, risk, and challenges. So how early career ocean professional could contribute? So by involving the research in and innovation like related to carbon dioxide removal technique, as well as by improving the models in terms of carbon dynamics, as well as by collaboration and further technology and capacity building, and by doing some extra curricular activities as well as workshop organization. Thank you. Okay.
Just
Okay.
can you take me to slide number 5?
Which one?
Slide number 5. Before this, yeah. You used your pi control, right? I mean, pre-industrial date.
Pre-industrial.
Pre-industrial date.
These are the observed temperature. So from observed temperature, what they did, they calculated the average of 1850 to 1900 temperature. With respect to that, they have plotted how much is the anomaly with respect to that time.
Which observation?
These are observational data.
Ah,
Yes.
okay.
So this is not temperature. This is global temperature anomaly. Clear? This is with respect to how much temperature has been increased with respect to, you may say, from 1900.
Question as such is, I just have a doubt. Thank you for your presentation. When you talked about and alkalinity
Enhanced.
enhancement and the fertilization techniques, you did not mention about like the impact it could have on the biodiversity and the ocean life. And I'm happy you discussed the risks and the challenges to alkalinity enhancement. But would that also not impact like the ocean life, or is there like work being done on knowing how it impacts? Or
It may impact. So that's why we are doing these things in the our laboratory based experiments, like mesocosm experiment. So what we do, we collect 1,000 liters of the seawater and we bring to the laboratory, and we are manually adding some minerals. So we are manually increasing the alkalinity, and we are testing how it is going to affect the carbon nitrogen fixation, and how it is going to affect the diversity of different phytoplanktons as well. So we are testing everything here. So this process is in underway. Yes.
Sir, I have a question, and you talked about different carbon removal techniques like ocean alkalinity enhancement and all. So, how do you set the boundary conditions, sir?
And boundary condition means
I mean, ocean dynamics is very complicated. I mean, if you put the alkaline solution also, I mean, how long it will stay in the ocean or it will get mixed up?
That is the challenges, monitoring, response, and verification. So we are working in that direction and we are testing. So uh, let's see how it could be solved. So that is a big challenge. If we are adding some mineral to the ocean, how will be able to monitor and how will be able to verify how much carbon dioxide has been removed, and all these things are challenges.
So was your question related to modeling ocean alkalinity enhancement, or what was your question related
mean,
to? When you asked about boundary conditions, I meant.
Actually, we'll be focusing a particular area for these solutions, right? So, I mean, if you apply that solution there, I mean, due to complex ocean dynamics, how long, I mean, what will be the impact? I mean, how can you value the impact? That's my question is.
Okay.
My question is, I understand that you're asking about what could be the impact, but I am asking, is your question related to observational aspect of ocean alkalinity enhancement, or are you talking about modeling the solutions? So when you're saying
Observation.
solution, are you meaning mathematical solution, or do you mean the English word solution?
Observation. Observation.
Okay, okay. No, I misunderstand. I misunderstood. Yeah, go ahead.
So yeah, this okay. Okay, okay. Yes, yes. Okay, okay. So to increase the crop production in the field or agriculture land, what we do? We are adding ammonia, not ammonia, urea, I think. Urea or some potassium or phosphate based minerals to increase the crop production. Why we are adding ammonia or phosphate or anything else? Because photosynthetic does not happens only in the availability of the carbon dioxide plus water. They require other nutrients like nitrate and phosphate to make protein as well as ATP. So everything is required. So what happens? So we have plenty of carbon dioxide, but in the ocean, particularly in the low latitudinal region, nitrate concentration in the surface ocean is very low. Okay. If nitrate concentration is very low, that is readily gets utilized by the phytoplankton. So we need excess additional nutrient supply to increase the primary productivity of that phytoplankton. So that's why we are adding some fertilizer to here to increase the primary productivity in the ocean. So aquatic animal health, you may you may say with this method as such doesn't have any issue, but there is one restriction, like primary productivity is not that much uh, linearity with the addition of any nutrients. Like if you are keep on increasing the nutrients, primary productivity will not keep on increasing as you are adding the nutrients. After some time, that will be saturated. So primary productivity will not increase. So that method has some certain limitation. Just adding the nutrients, you cannot remove all this carbon dioxide from the atmosphere. So that has restriction. But anyway, this method doesn't involve any bad things. So eutrophication could be a issue, particularly in the coastal region here, if you are adding excess amount of nutrients. So first of all, we need to um, test these things in the laboratory. What or the concentration of the nutrients in the particular given region. Depending upon availability of nutrients, we will add additional amount of nutrient. We need to know about all those things. We cannot add anything blindly to the ocean. You are talking about coastal ecosystem, but open ocean is not so much dynamic in terms of change in nutrient concentration. Yeah. So this method mainly will be applied to the open ocean, because coastal ocean is already getting nutrients from the terrestrial discharge as well as submarine groundwater discharge. So the primary productivity is not the issue in the coastal region as such, but it's a big issue in the open ocean. Yeah.
Actually, I have some different opinion regarding this ocean fertilization for in Indian seas context.
Okay.
So if we think about Indian seas, say if we look at the west coast of India, we have naturally happening ocean fertilization every year, like this upwelling.
Mm.
This happens every time, every year.
Yes.
But the consequences, every time we see there is one after another harmful algal bloom comes back, right?
Yes.
So how you can ensure if you fertilize our seas, it will not lead to harmful algal bloom? The first question is that. And if we look into the east coast of India, there the main challenges is the turbidity.
Yes.
Even though there are nutrients, but organisms may not be able to utilize it due to less penetration of sunlight.
Sunlight.
So how ocean fertilization will work in Indian context? Because I understand this this concept has been developed in temperate seas, where the food chain is very, very simple. Like if you see Baltic seas, Arctic seas, their food chains are very simple. But in
Yes.
India, Indian seas are very complex, right? So the moment you fertilize the ocean, the first organisms who is going to face this microzooplankton, because they depend on the picoplankton, nanoplankton. So if you fertilize the oceans, then the bigger chain phytoplankton, say for larger algae, they will grow faster, right? If you
Yes.
have more in nutrients. So what is your comment on that?
Agree on that. So that's why these things are applied to the nutrient depleted region, not the nutrient deplete condition. Like you might like we know coastal upwelling is happening around along the western coast of the Arabian Sea. So we are not going to add the nutrient in the upwelling region because we are already getting excess amount of nutrient in that region. This method could be only applied in the open ocean region where upwelling is not happening, whereas most of the upwelling is happening in the coastal region itself. So, whereas if you are talking about coastal regions, so coastal region does not require much addition of this nutrient. And this method was also tested in the southern, what I guess in the southern ocean. So there we have nitrate and phosphate in the that is known as high nutrient, high chlorophyll regions. So high nutrient and low chlorophyll regions. So there we have excess amount of nitrate and phosphate, but still we have very low productivity. So because that region is mainly limited by iron. So they have tested these things there. So they didn't find very helpful by applying this method. So there is some consequences.
Like to add a comment here.
Yes.
In my previous company where I was working, there were research on ocean iron fertilization. So I got the chance to do an extensive amount of research. So it seems that we need to first study the iron biogeochemistry, because iron has a weird way of cycling.
Yes. Yes.
And also some of the diatoms there, the phytoplankton there, also, or there are some bacteria which can adhere to the iron, and that's
Yes.
how iron naturally stays afloat. What happens is if we are adding iron sulfate, a simple acidified ferrous sulfate addition, it will have it will face some challenge staying afloat, because immediately it will sink, because once it comes in contact with the atmosphere, it will oxidize to become ferric sulfate,
Yes.
and it
Yes.
will
Yeah.
immediately sink.
Yes.
So the challenge is to keep it afloat, so that uh, there is no overestimation of adding iron sulfate, that
Okay.
okay, it's not there, we cannot see the signature on the surface, so we keep adding so that we see some change. So that will become very dangerous, and already it has faced a lot
Yes.
of embargo. There's been a huge hue and cry from the environmentalists since 2009. I think you're aware of that.
Okay.
So it's good that the discussion is on again, because I've read Dr. Smetachek's article, which was that seminal paper done in Southern Ocean, where they saw
Yes,
the
yes.
bloom in for at least 14 to 49 days. They saw that bloom happen, and then it sank. So that's, I think, the method
Yes.
can sustain only if there is an extensive research done on the iron biogeochemical cycle itself.
So these things are required. So there are certain limitations that
Yeah.
this is the reason ocean
The
building
first
can
thing
be.
US EPA is going to jump on board, and
Okay.
they will say that
Mm.
why are you adding the intervention that requires a lot of hurdles to cross. Thank you. Absolutely. I'm referring to the
Elva regions. Mm.
I'm referring to the Lohaf experiment.
Okay. Thank you.
Thank you.
Sorry, sorry. Here we have efficiency. How much dollar is involved to remove that much of carbon dioxide? So this is very helpful part. There are both techniques which involve the carbon dioxide removal in the coastal system as well as in the open system. So they have different advantage and as well as disadvantage. Like we have coastal blue carbon system, so we are sequestering more carbon dioxide if you are restoring that system. But problem is that uh, that cannot um, accommodate that much of carbon dioxide in that system. So that's why the open ocean seems to be the better solution for the carbon dioxide removal technique. So we have different methods while weathering and yes. Higher trophic level, and when the human condition, they might get. Yes, these things must have been tested. So still work is going on. If we are adding some minerals or nutrients to increase the primary productivity, what would be the consequences in terms of uh, elemental cycling through food chain, and how it is going to affect the oxygen condition as well as other biochemical condition of the ocean. So these things are still being researched. So these processes are underway. So that's why these techniques are very, these topics are very conflicting, like you may say, in terms of consequences. What would be the consequences? This seem to be the direct approach, but it's not as much direct. What is?
So when we talk about its practical aspect, how do we identify a location that it should be fertilized, or is it just the iron, or is there any another parameters you are considering when you find a location to do this in practical terms?
Okay. For practical terms, like if I will talk about 1 minute. Like if you wanted to remove the carbon dioxide by direct carbon capture method, probably you might prefer the coastal region. So you can actually find coastal storage as well. If you want to iron fertilization method, you might probably choose the open ocean. So depending upon the different CDR method, you may choose different ecosystem. So usually in the OA method, what we are doing, we are collecting the coastal samples only. So just we are testing how these things are going to work. Once it will be verified and how it is going to work, then we can apply this thing to the open ocean as well. Yeah. Yes. Yes, yes, we have different policies. So uh, international agencies are working on that already. So we have, so whatever projection I have shown, that those projection are mainly dependent upon different climate policies. So of course, we have climate policies to reduce the carbon dioxide emission as well. Yeah. Policymaker? Research communication, you may say.
Stakeholders. Stakeholders.
People who are doing research on this problem. Not us, because we don't have that expertise.
And regarding sewage discharge in the rivers as well as in the coastal regions, we have some environmental act as well. You might be heard the 1984 Act of the India regarding the environmental. So we have act as well as policy documents.
Yes, we have act, but whether we are acting on the act, that is.
Yes, yes, yes. That is the biggest fact.
India has phased out plastic, single-use plastic by 2021. Till day, we have single-use plastics. I'm very happy with inquiries that they are not using plastics, single-use plastics. But act is there,
Yes,
but it is our responsibility to act on the act.
yes, yes.
there any protocols that estimate carbon sequestration in intentional mangrove forest?
Sorry.
Protocols or guidelines to estimate the carbon sequestration, blue carbon,
In-
in mangroves.
Uh, I don't have enough knowledge about carbon dioxide sequestration in the coastal regions. So I'm unable to comment on this. How they are. Yeah. Yeah.
She works on it. So if you have a question to her, you might get
Yes.
join online.
Okay.
Yeah.
Thank you. Yeah. Okay. Thanks.
We'll be breaking for lunch actually. We have some 5 minutes before 1 p.m. Tarunya will distribute the forms to the fully funded participants so that they can fill up their details for the bank account details and all of that. And if you have questions, do ask her if you need any clarification or anything of that. And then once you distribute, you can take your time to fill it up. By the end of today, do you want that? Or by tomorrow also you can take your time, not a problem. And then we'll break for lunch.
Thank you. Place, date of time, place. Extra. Wow. ഇവിടെ ഇവിടെ ഇവിടെ
Or you have to attach the tickets also. Educate people well.
रेशिता
Hello.
आफ्टर आफ्टरनून ऑनलाइन है ना लोगों को बोलो 15 मिनट पहले ज्वाइन करने के लिए टेस्टिंग टेस्टिंग करना है ना
Okay.
हाँ 2 o'clock ना
So 2 o'clock is online physical.
ऑफलाइन ना ओके
And 2:30 is the online.
After
one.
that, 3 talks are off.
After that, one after the
online.
other is after 3 talk. One after the other is on.
I already given another slot and everything.
ये है ना
हाँ
Are these three?
आज फ्री है ना
हाँ one after the other. The first stop is physically raising. I am bored of it. Basic, basic.